Swayam Prabha. Digital India. Educated India.
Dear students, now that we are familiar with the concepts of linear programming, duality theory, dual simplex, and integer programming, we should move ahead with the next class of algorithms that we broadly call as evolutionary algorithms. First in line in the evolutionary algorithm would be genetic algorithm, but since this is the first introduction to the topic of evolutionary algorithms to many of you, let us start with a very brief introduction that what these algorithms are and how do they differ from our typical linear programming problems. So when we talk about evolutionary algorithms, these evolutionary algorithms are typically nature inspired meta heuristics. So, what are these three words? Let us pay emphasis to that. So, if you have paid attention to how ants move or how birds flock or how species evolve, all these three are fairly natural processes, but you always find that there is certain system involved with these particular processes. For example, whenever ants move from one location to another, one ant would leave the trail of what we call as pheromones. Other ants will find that this is the most optimal path to go towards the food or forage, and that is how you would see that a straight ant line will form as the movement is happening. Similarly, birds have a certain flocking pattern, that is, the weakest bird may be at the center and others would flock around that, and if they are going from one point to another, either for migration or either for forage, they would not be moving abruptly in all direction if they are moving around as a group. Of course, when individual birds will move, they may appear that they are uh, moving around randomly, but when it moves as a flock, we see that an emergent behavior is coming out of the entire system. Similarly, how species evolve, that there is a population out of these two population out of these population we have two parents mate, as a result of which an offspring comes into picture. If offspring would have the genetic material which can be decoded back to the parents. However, certain mutations can also happen in the offspring genes, as a result of which we can have an entirely different offspring coming out of this particular process, and as a result of which, with these continuous sustenance of mutations and reproduction, we would see that species have of course some signature of parent material, but it would be start getting very different. Now, if we put all this understanding together, we just talked about three very simple examples that surround us, but they give rise to these nature inspired optimization algorithm, because all the natural processes would like to keep their energy losses to minimal when they go for food or forage, and that is where scientists saw an opportunity to develop a class of methods what we call as nature inspired meta heuristics. Now let us talk about the word meta heuristics. Meta heuristics essentially are search based algorithms where instead of writing our equations in some differential form, for example, or going for the exact solution, we evolve from some initial state I. This can be totally randomly chosen. Then we iterate and we try to converge to optimal value. Now, we do this iteratively. So, depending upon how much iterations we have, we always tend to converge. That would be a better word, because there is no guarantee that once our entire iterations are over, we have actually converged to a finite point, because we are not going behind an equation in differential form or a simplex kind of tableau where certain variable has to enter and certain variable has to leave. There is always going to be some random seeding when we talk about these methods, as a result of which the end answer that we get is near optimal, then optimal. And of course, I am talking about those particular situations when your algorithm or iterations do not get stuck at certain point. That answer can be even far, far away from the optimal. And we may have no idea to trace that how far are we from the optimal. So, but broadly speaking, that when we put all these steps together, that is evolution to near optimal solution, with some algorithm, we are looking at heuristics and meta heuristic approaches. But since they mimic some biological processes or biological evolution, we call them nature inspired meta heuristics. In most of the cases that we are going to talk about in these evolutionary algorithms, we are going to involve populations of solution, because we don't know what is the right answer. So what we do is that we generate some tens to hundreds to thousands of population randomly, and then see that which particular subset of population is the fittest to survive for next iteration, and we keep on eliminating the weaker population, as a result of which the next subset that we get in comparison to the initial subset is better in terms of performance towards meeting the objective function. So this also relates, we will touch upon that later on, relates to some aspect on this Darwin's theory of evolution, what we call as quote unquote survival of the fittest. I am not saying that we are going to copy or replicate exact biological behavior, because that may be very difficult for us to encapsulate in the equations or mathematics. But this is inspired by nature. Sometimes it's also reverse engineering, that we developed an algorithm and then we realize, oh, hey, this is looking very much similar to a biological system in action. So we may name that particular algorithm after a particular biological process. So we should be very clear that this is not exactly copying the nature, but getting inspiration from that and developing mathematics, algorithms, and stepwise processes around that. And where these algorithms are useful, because we have already learned so many optimization approaches, then why do we need a new one? So you might have realized, whenever we were talking about any optimization approach such as Lagrange multipliers, we always wanted our objective function to be fully differentiable. When we were talking about simplex methods, we wanted our constraints and objective function to be linear, feasible, etc. So what is the problem there is that nature would not be confined by these set of rules when it is defining optimization problems for us. Same thing happens in various infrastructure decision making, where a lot of processes are complex, non-linear, multi-objective problems exist, and we do not have an exact functional form. Forget about the differentiability of the functional form. We just know that solution has to be good, better, or best, but we really do not have any functional form to capture whether what is going to be fully differentiable and so on. And that is where these evolutionary algorithms come into picture. So again, just to put that into summary, is that classical methods are also very good because they guarantee the optimality. So, for example, if you express your objective functions and constraints in a linear programming form, and if you are going towards a feasible solution, it is guaranteed that whatever solution you are going to get is a global optimal solution. However, that is not necessarily the case with evolutionary algorithm, because they may take you to the local optimal, or they may get stuck into some local minima, and there is no guarantee that they would be coming out of that. So whenever possible, we try to go with the theory, use theoretical guarantees, and get to our answers. However, whenever we do not have these structured equations or problems, we often go with the evolutionary algorithms. Uh, Now, when we talk about classic methods, we already learned that whenever we were talking about some toy examples, we were dealing with five constraints and six variables and so on. And we also learned that when you try to do these particular methods in graphical form, they essentially take the form of polytope. While making a polytope on a two-dimensional graph is easier, but when we talk about higher dimension, we lose tractability of the system, both in terms of visualization as well as in terms of mathematics. So these classical methods become complicate overly complex for large scale or highly non-linear systems. Because if you recall, when we were talking about Lagrange multipliers, we introduced a test to check for necessary and sufficiency condition. While checking necessary condition was easier when we were talking about multivariate space, the moment we started talking about the sufficiency condition, we were talking about Hessian, we were talking about checking for semi-definite positiveness, semi-definite negativeness, and so on. So it becomes quite involving mathematically as we keep on going towards more and more non-linear problems. And most importantly, we require strict formulation. Mathematics should be written in a way that objective function is convex or strictly convex, and it is differentiable throughout, which again may not be easy to achieve in many of the real world setting. And that is where evolutionary algorithms equip us with flexibility. They are population based, so there is a better chance of a global search, and there is no need to have mathematics written right or derivatives to be existent. So, some of the commonly used evolutionary algorithms that some of you might have already heard about includes genetic algorithm. This is going to be our point of discussion today. We are going to cover mathematics with examples as applied to simple problems as well as infrastructure problems in detail. In our subsequent lectures, we will talk about particle swarm optimization. I already gave you the example inspired by a bird flocking or fish schools moving in the water. And here a swarm of particles will adjust population in the search space based on their cognitive intelligence as well as social intelligence. Now, this is simply fascinating that how these things that we often use for decision making are actually used in optimization, and that's where we have to learn these and apply these to certain systems that we are going to deal with. And then we also use something called as differential evolution, and other things are evolution strategies, where we also include self-adaptive mutation rates, and these are well suited for continuous problems. In this particular course, we will primarily focus on GA, PSO, and I would encourage readers to use the similar philosophy to learn more and more of more and more of nature-inspired approaches for optimization as and when use arises. But the good thing about these approaches are that if you learn one or two of them, you would be able to see a very similar structure following across multiple evolutionary algorithms. So we will spend maximum time and energy on the two key approaches that are popularly used, which is genetic algorithm and particle swarm optimization. So let us begin our focused discussion on genetic algorithm. So here is a broad philosophy. As I mentioned, it is inspired by the Darwinian evolution, that is survival of the fittest. We will spawn some initial population. These population will make offspring. These offspring may or may not go mutation. But for each of these elements of population, what we will call as chromosomes, we will keep on calculating something called as fitness score, and based on fitness score we will keep on retaining or eliminating certain members from the population. Uh, as we are using word population again and again, it makes genetic algorithm a population based search where many candidate solutions evolve over the time. It is a balance between exploration and exploitation. These are two very important words whenever we talk about search based algorithms. When I say search based algorithms, I mean that I will be searching for my solution in some lower bound and upper bound. This lower bound and upper bound could be minus infinity to infinity. I have, if I have lot of computational resources, or it could be based on some understanding of domain that hey, this particular variable only varies from minus 5 to 5, for example. Now I have two options, that I can keep on dividing this search region into number of finite grids, and I can keep on putting all the values possible to get my answer. But you can really imagine that how computationally prohibitive it is going to be, because I have to now choose size of the grid. I have to ensure that my solution is somewhere between, within the resolutions of grid that I have chosen. Not that these methods are not used. Methods such as Newton approximation or bisection approaches are typically based on searching within these particular limits. But here again, if you have to search over much larger domain, it becomes computationally prohibitive. And more importantly, you are making computations at a point which is not helping you improve the solution at next point. For example, if your optimal solution is here and you have started finding calculations from here, that is, I will keep on going from one point to another point to another point. Of course, at some point you will reach optimal or near optimal if you have infinite computational resources. But you see that all the points in blue are information or that you have generated, but it is not at all useful because it does not even tell in which direction to move. So that is one reason these evolutionary algorithms gained lot of popularity over these grid search methods or bisection methods. So that is where this word exploration comes into picture. That genetic algorithm gives us gives us enough tools to move from one area to another area at much faster rate, which grid based methods may or may not necessarily equip us with. Similarly, it helps in exploitation. So for example, if we say that our solution now exists in this particular region, we will keep on evolving our best of the candidates over the time until we hit the bullseye or reach our optimal answer. Now, exploration and exploitation is actually one of a major empowerer of these evolutionary algorithms, because most of the evolutionary algorithms, they explore new areas to find their optimal, and they also evolve as they go towards search for the optimal, which we broadly call as exploitation. And genetic algorithms have been widely used in engineering, scheduling, resource allocation, and we will also look into a few examples, one numerically solved example and few anecdotes that how it is being used for engineering decision making. So these are a few examples specifically where GA is used in infrastructure. You can find lot of research articles where people have actually used, operationalized, translated it into products. For example, in transportation, we are always interested in network design, that what should be width of the road, what should be width of the pedestrian way, what should be width of the shoulder, and so on. Now, writing a neat mathematical objective function for such pragmatic situation may not always be possible. That is where genetic algorithms would be helpful. Similarly, for traffic signal timing, route planning, which again happens to be fairly non-linear problems because multiple components are interacting with each other in the system, genetic algorithms come quite handy, where you cannot always write neatly the underlying linear or non-linear differential equations. Then comes to risk and resilience. This is one specific example that we will do on floods in this particular discourse, that how many pumps we should place in a city to minimize the dollar value losses or risk, as well as to have minimal costs of the pump, because answer to every problem in optimization is infinity, that put infinite pumps, your risk will be zero, but each pump is also going to have a cost. So there is always a trade-off between how much money you would save by averting the risk, and versus how much money you have to invest to avert that amount of risk. Then budget allocation is another area. When you have multiple competing objectives within the project, multiple activities that compete with each other in terms of prioritization, that is where genetic algorithm again help. And in terms of structural optimization, it is used to minimize the cross sectional areas of various structural members, as well as maximizing load bearing capacities of various elements that we are considering. Now that we are clear that what this genetic algorithm entails, let us talk about what are the core steps that would be involved in genetic algorithm. So, like almost all evolutionary algorithm, first step would be initialization, because we don't know where our solution is. We may only have information about grid. Our optimal solution would be somewhere here, but this is the only information we have in some of, let us say this is some function fx is equal to x square, and problem is that we may have to minimize this. Now mathematically you would know that put x equal to 0, you should have your answer, this is the minimum value. But let us think about it in an algorithmic way. You do not know where this is, so what you will do, you will initialize your best guess here, and then you will see that, oh, there is some difference between this, and again this difference is going to be relative. For example, if there is another particle that you have initialized here, it would have lesser of a difference from optimal. So you would clearly see that if this point is a, this point is b is having better value than a, because you do not know the ground truth here. You do not know as an optimizer that red one is your target. You have to find it during evolution of your algorithm, that after what point I cannot further improve my solution. So, but there is a clear motivation that now B tells to A that, hey, I have a better value in terms of whatever objective function you have than A. So you should start moving towards me. And this will keep on evolving in a way that there is an individual intelligence involved, there is a cognitive intelligence involved, and both of them are also communicating with each other. But more importantly, what we have done here is that we have to still initialize certain points or put some seeds at t equal to 0 that would evolve in time. So this initialization can be done using some probability distribution. For example, we already learned about normal distribution, uniform distribution, etc. But one of the most common ways to do this initialization is uniformly you create some population, certain points randomly all over the space of significant size. That is important. You need to have sufficient sampling to initialize your algorithm, because if you have finite number of points that you have initialized, like is 1 or 2 or 3, they may not have enough impetus to evolve, because they may feel that, I'm already the best in the domain. So you need to give competition to these points even when you are doing some random initialization. That is where initialization is very important, to have a critical mass for enabling system to evolve toward optimal. Now next thing is fitness evaluation. We already spoke about fitness evaluation, that is each point is going to have some fitness score. So if A is farther away from actual optimal, it is going to have lesser fitness score in comparison to B. So we assign this fitness and evaluate it in some descending order, who is the fittest and who is the weakest, and based on some thresholding we can keep on eliminating the weakest of the solution. Then we have to do selection. As I already said, you started with some n number of members in your population. Out of them, you arrange them in some descending order. But then you have to now cull or remove those particular members who are below certain threshold of their fitness. So that is what we will call as selection. Now, next point that comes into picture is crossover. We would only let fittest of the members in population produce an offspring, because if two members are fit, probability that the resulting offspring will also have better fitness is higher in comparison to the offspring coming out of two parents who are relatively less fitter in comparison to the rest of the population. So that's where crossover will happen. After crossover, we also introduce mutation. That is, we randomly pick one or two locations and flip those particular values. So we may make 1 equal to 0, 0 equal to 1. Of course, this is nature inspired method, that mutations are part of the nature. But the bigger reasoning behind having mutations enabled in genetic algorithm is to ensure that our solutions are not getting stuck at certain point, because everything from 1 to 5 is happening through some random seeds that we have generated. Now, what if the randomization is poor and there is no opportunity to get out of it? That is where this mutation comes into picture to change certain values arbitrarily as algorithm is evolving, and it does help us speed up the convergence to optimal. Finally, we talk about the replacement and termination whenever we reach the best solution. That is, over the time we are reaching certain points, and what may happen is that you started with n number of population which were primitively part of your sample generation, but now offsprings are even better than the parents. So what we would do, we will replace those parents by the offsprings and let offsprings further produce the new offsprings and so on. So that is where replacement comes into picture. And after that, we need to have a termination criteria, because these algorithms may take you to the near optimal but doesn't guarantee that there would be an optimality. So you would put some number of iterations for steps 1 to 6 to happen. And once these iterations, number of iterations could be 500, it could be 1000, it could be 1 million and so on, depending upon whatever compute is available to you. Or you would say that if change in my fitness is less than some threshold, let us say 0.001, then algorithm should terminate, and this is the best possible solution I will get. So I have elaborated on all these terminologies that we discussed earlier. You can take a moment to go through the uh, text about all the terminologies. So here it's about initialization. Then about fitness evaluation. then about selection, then about crossover, then mutation, and replacement and termination. We will, of course, put all these terminologies to use in two examples that we will do. So, it may give you more clarity that we are going to have once we solve these problems. So now let us define the terminologies that we will use within these algorithmic steps. So first one that we are going to use is gene. We will call the entire code as chromosome. This can be coded binary, something like this. It can also represent some identifier 1, 2, 3. It can also represent how many number of units 3, 4, 6. This can also represent some time factor, that is whether 3 minutes, 4 minutes, 6 minutes, and so on. So it really depends on what rule you are going to use to define your sequence of genes, and sequence of genes would be called as chromosome. Now, these genes value would directly influence a specific part of the solution, because as I said, this could be number of pumps that we are installing in first building, second building, and third building. So if we are installing 6 pumps in third building, and cost of pumps there are higher depending upon size or geometry of that particular building, this gene directly is going to also influence the final costs that are involved. That is why these genes have a significant role in determining overall behavior of the chromosome unit. So as I already mentioned, this chromosome would be assembly of these particular genes put together. So one would be individual gene 0 individual gene, and when I put these together, these become 1011 and 00. And we will also have something called as array of integers like 253. Real valued numbers are also allowed. So there is typically misconception among students that whenever we are doing GA or any genetic algorithm related optimization, it has to be binary encoding. Of course, binary encoding is easier to handle, but that never prohibits us from going for non-binary encodings, because as I mentioned earlier, that these algorithms are agnostic towards math, differentiability, in what particular domain they are exploring the solution, because they would evolve. Next solution would be better than previous one, and so on. So this really depends on that what kind of infrastructure problem we are trying to solve. For example, in case of infrastructure, it could be number of lanes 210 to add in each road segment. That is also a possibility. Uh, and also sometimes you can also define the constraint on a particular chromosomal material. For example, you may say that even if I am making 3 roads, total number of lanes cannot exceed 6. So only those elements of population or only those chromosomes would be considered valid whose genetic material summation is less than equal to 6. It could be exactly equal to 6. You can also make it greater than equal to 6. And it is again very human, nature inspired, that we say that number of chromosomes are fixed. Similarly, genetic material is hard coded, and so on. So we try to take that particular inspiration with enough flexibility that how we are going to design our bio inspired system. Now coming toward population, set of chromosomes would be called as the population. So for example, you can have 20 members into your population, and they would look like 1001001010111 and so on. I can have some n number of combinations here. So this is going to be my population in this context. So if you have larger population, it of course means more diversity. You have more opportunity to find even better solution than the previous one, but it also comes at higher computational cost, because then you are evolving n number of population members simultaneously, or selecting, terminating, and so on. So it becomes computationally a bit expensive. And what we see that over generations, these populations are not stagnant. You initialize from here, but these populations also evolve by producing offspring or by mutating, as a result of which weaker solution get replaced by the stronger offspring. And that is where the algorithmic rules come into picture, that you just doesn't say that now I have defined the initial population, keep on mutating. You have to keep a check and find mechanisms to eliminate your your not so fit population members. One typical way that we will do this particular elimination is something called as roulette wheel. If we go to casino, although I don't encourage that, but you would see roulette wheels in casinos where a dice is rolled, and if it stops on a particular number, there are certain payouts, but certain numbers are marked more than the others. So there may be five number of fives, four number of fours, etc. So chances of getting fives are more than getting your dice getting stopped at four. But that also means that 5 will have lesser payout in comparison to 4, because probability of getting 5 is much more common than 4 itself. But this entire algorithm of doing some weighted selection using probability is called as roulette wheel algorithm for selection or elimination of certain entities. Now, if this is clear, let us move to the next term, what we call as offspring. So what happens here is that new chromosomes produced from the parents uh, via crossover and mutation, and this entire process is encapsulated in word offspring. Again, a very nature inspired word. So for example, if we have two parents 312 and parent 2 is 203, we can at first place take the genetic material from parent 2, at second sorry, this comes from parent 1. First element comes from parent 1, second element comes from parent 2, and third element again comes from parent 2. So child is going to have the genetic encoding of 303. So this can be the rule that first element would come from parent 1, rest would come from for parent 2, and I will keep on following that as I evolve my solutions going forward. And these parent 2 and parent 1 can also interchange their rules. So I can have two potential candidates for offspring in terms of their genetic coding, and then I assign the costs to these two offsprings that I get. Once I have that, at each point I will be calculating the fitness function. So for example, in our road example, there are three segments: segment A, segment B, and segment C. If I provide two lanes here, I provide one lane here, and I provide three lanes here. If this is a village road and this is highway and this is a forest road, so I randomly said that two lanes in forest, one lane in highway, and three lanes in village. You would immediately see that this particular design is going to lead to some congestion in comparison to one lane here, three lanes here, and perhaps two lanes here. So I don't know what is the absolute best here, but I can always see what is the relative best. Or I can say that solution 2 is having more fitness than the solution 1, and it can be number of vehicles stuck on the road or average speed on these particular roads. So fitness can be defined depending upon whatever context we are going to have, and that is where genetic algorithms offer us much flexibility to deal with unstructured objective functions or relative objective functions, where we can say that A is better than B in the relative sense without explicitly writing the mathematical equation for the same. And this is typically you would see in many infrastructure example, that minimize total cost, maximize reliability. Again, reliability is going to be sort of a vague word, and I am not going towards theoretically guaranteed maximization or minimization. All I'm saying that nearly maximize. So that's where the word near optimal comes into picture. Nearly maximize my answers. I do not care about exactness. I care about the best approximation of the problem at particular disposal, because I don't know the objective function. That is why I cannot ask for the exactness if I don't know the exact objective function. And what it does is that this fitness gives us some hierarchy, that which population members are better than the others, and then we will find ways to give some score or probabilities to select more fitter the fitter members more frequently over the unfit ones. Now let us try to put all these concepts together into this very simple problem of maximize fx equal to x square, and we have been asked to find the answer in the domain of 0 to 15. Now you see there is one clear difference between linear programming problem and genetic algorithms, that in linear programming we will never specify the bound. All we will say is x is greater than equal to 0, algorithm should find it for itself where my solution is. In this case it's not a linear programming problem, but for that matter I am talking about any structured programming or structured optimization problem, but here I have to specify the bound where it should be looking for a solution. You already know the answer. If it's a maximization problem, answer has to be 225, but let's not worry about the specificity of answer, but let's worry about the approach, that how we will solve it the genetic algorithm way and really see whether we will converge to 225 or not. So what we will do is that we will encode all the numbers between 0 to 15 using a 4-bit binary representation. Again, this is just a representation. It should map back to the original number. Here, it happens that these representations are actually binary representation of these numbers, but that doesn't really matter in our discourse of discussion, because as I said, these chromosomes can be numbered as per your own rules, but you should be able to map these chromosomal code to the original entity. So here I said that x equal to 0, x equal to 3, x equal to 10, x equal to 15 are coded in some sense or another, and my fitness function is fx equal to x square. So for example, if you say that, hey, the chromosome here looks like 0011, I would immediately map it back to 3, calculate my fitness score, which would come out to be 9, and so on. So what I will do, I will follow those 7 steps very systematically. Whatever I have discussed in earlier discussions, I will initialize 4 chromosomes. I can also initialize 10, I can also initialize 5, etc. But it's a very small toy example. So let's keep our numbers fairly small to get full sense how these numbers change or evolve over time. So I generate 4 chromosomes randomly: 0000, 0101, 1010, 1111. The moment I generate them, I map them back to the original decimal values, which comes out to be 0, 5, 10, and 15. And you can also have other numbers sandwiched between them. We will also see that later. That really doesn't matter. It just happens that all these 4 numbers are at the interval of 5, but there is no systematic thinking here. It's just that I generated these 4 numbers and mapped them back to the decimal places. I do the fitness test and say that, hey, this x equal to 0 gives me score of 0, next is 25, next is 100, and 225. As I am calculating these fitness for each of these iterations, I will also calculate sum fitness. So in this case, sum of fitness would be 0 plus 25 plus 100 plus 225, which I think should be coming out to be 350. You can check it for yourself. Now, this would be useful whenever I have to sample in some probabilistic sense. Now it is very clear that I should eliminate these two populations. These two members of the population, because they have the least fitness. However, I will not do it just by looking at the values. I will do it in the probabilistic sense, so that I always maintain the diversity as my solution evolves. So I would not just say just eliminate these two. I would say that assign some probability and probabilistically find a way to eliminate that. Again, a nature inspired thinking, that there is a saying that survival of the fittest, but that doesn't necessarily mean that the weakest is always going to get eliminated. So to reflect that, what we do is that we assign some probabilities of selection, that if somebody is 0 fitness, chances of its selection is 0 divided by sum of the fitness, which we calculated as 350. Second case, 25 divided by 357%, 28.6%, and 64.3%. You clearly see that even this Roulet will is giving more weightage to the fittest member. However, this not so fit candidate also has 7% of chance to get selected. So if it gets selected, it gets selected. The algorithm will continue from there. Now, one thing to remember here is that sometimes students don't know how to sample it. If I say 7.1, etc., all we do is that we generate a uniform number between 0 and 1. If that particular uniform number is let us say that the uniform number that I generate here is 64. Chances of this particular number to be on this particular side is that if this number is less than the number that I am generating, that particular number should be sampled. So this selection happens from a uniform number generator between 0 and 1, and you see whether the number that you have generated uniformly, how it compares to the original number, and you decide to select it or not select it based on this uniform number sampling. And this is a pretty standard practice whenever you have to do any random number sampling from any distribution or any probabilistic method, and so on. So now what happens is that, let us say that we keep it simple, and the two chromosomes that we finally select are 1111 and 1010. So these become the parent 1 and parent 2. So what these parent 1 and parent 2 will do? These parent 1 and parent 2 will make an offspring. So here we define a reproduction rule. We say that we will cut the parent 1 first two genetic codes and add it to the parent 2 genetic code, and these parents can also interchange their relative position. That is, parent 2 can become parent 1, parent 1 can become parent 2, and so on. So one child is going to have the chromosomes like 1011, and child 2 is going to have the chromosomes like 1110. So now we know that 1011 maps to 11 and 1110 maps to 14. So now what we also do is that we take one of these offspring randomly and mutate it with some very low probability. This probability of mutation should be very small, otherwise your solution may get unstable. But here, to show that how it would work, mutation would force this 0 to become 1. It could also force this 1 to become 0, and so on. But this is happening with very little probability. This mutation is happening with probabilities of order of 1 to 5%. So what it does is that it just helps us converge to the optimal value faster. You can always argue that why mutation? Yes, you can drop the mutation, algorithm will still learn and evolve, but chances or risk that it may get stuck at certain non-optimal value also increases if you are not having enough diversity in your population or in the offsprings that you are getting out of this stepwise exercise. So what we do is that now we have three offsprings. Two came without mutation and one we mutated, because that is also one of the possibility that could give you an answer. So we don't say that we will discard one of the offspring that has mutated in our original solution. No, our idea is to have as diverse of population that is possible. Again, it's a nature inspired solution, not just the natural solution, because in nature what will happen if a gene mutates? It will of course take a newer value, but here we retain the offspring's original values as well as the mutated values. So x equal to 11 gives us score as 121, x equal to 14 gives us score as 196, and x equal to 15 gives us score as 225. So over multiple generations we would see that higher x solutions accumulate because they yield x square, and our roulette wheel selection will ensure that values closer to x square get selected again and again. So what we see that typically GA converges near x equal to 15. Now, a note of caution: you might have sensed that when I set up the initial population, I had value at 0, 5, 10, 15. There is no rule that values have to be equally spaced. I could have also sampled x equal to 3, x equal to 6, x equal to 13 at some uneven spacing, and my algorithm would continue to evolve in similar fashion, and doesn't matter how I initialize my initial population with some rule, without any rule, I would expect in most of the cases I will converge toward the same optimality doesn't matter what was my initial population, as long as I am following the rules that I have set for entire evolution systematically. So eventually, as I said, that in each of these particular cases, you would get an answer closer to 15 if you keep on evolving, and then after certain point you would have 1 1 1 1 1 1 1 1, and you would see that solution is no longer evolving. Offsprings are identical to parents. All these values are fairly higher than all the previous solutions you got, so you can now easily terminate your solution in this particular case. Now, this was a trivial problem. Why trivial? In the sense, you already know that in domain of 0 to 15, put x square to be the highest value, you will get your answer. So, indeed, this was a trivial problem, but if you notice carefully, it demonstrated the concept of encoding. From zeros, we went to binary space. 0 became 0, 1 became 1, but 2 became 1 and 0, and combinations thereof. 15 became 1, 1, 1, 1. So encoding is very important part in genetic algorithms, because if your encoding is right and clearly mapped to the decoding vector field, you would be able to keep track of the costs and profits if it's an optimization problem in much neater sense. It also demonstrated how to evaluate fitness when you know the function, objective function itself, and it also demonstrated concepts of selection, crossover, and mutation to evolve the solution. Now, this particular example had nothing to do with infrastructure, but it gives a strong foundation to apply to infrastructure kind of problems. So, a quick recap: we already learned about that these find usage in transportation network planning, for example, where to build new roads, how to time signals, and all of them are fairly unstructured problems. How to design a bridge, what is the minimum cost, material cost, safety constraints, evacuation route planning, that which particular route we should assign whenever flood is propagating or some other disaster is propagating, that minimize congestion within the city, and also resource allocation, that how limited budget across multiple projects can be efficiently allocated. This also applies to constrained unconstrained program problems also. Why? If you have a constraint problem, the genetic material you provide can be binded by those particular constraints. So it really depends how creatively you can think about your optimization problem and relate it to the methods that you are working on with. And that's where we say that sometimes in optimization, it's not the algorithm that is the bottleneck. It's the creativity and thought process to put a particular problem into the perspective of optimization that is the biggest bottleneck. So, as I said, that we can also have these chromosomes bear something called as non-integer values. So, if I am doing some phase timing for signals, let us say that there is a there is an intersection, and some vehicles, and there is a red light that I have to install, and I have to decide that what should be at that when this signal is operating, what should be the green time in this direction, what should be the orange time in this direction, what should be the red time in this direction, and so on. So this becomes a transportation problem. So all of them, as you can see, are strongly coupled with each other. That because these colors of signal, they are guided by transportation engineer or traffic engineer, but timing has to be decided optimally so that congestion is minimized or queue lengths are minimal. So I have some quantifiable objective function, that if length is longer in one situation than other, of course it's not an optimal signal design. And you might see around places or cities, most of the time signals are timed in ad hoc sense, as a result of which you would see there are long queues on one side and other lane is completely empty. And that is where these algorithms, if applied in right spirit and at right place, can actually solve the problem over time. More importantly, these algorithms have capability to learn or evolve with time. So if traffic situation changes or if timing of road usage changes, you can have different times at a particular intersection at different intervals. So very simple method can indeed be very, very powerful to solve the problems that haunt us almost every day. Again, there can be n number of creative visualizations. So another example I put here is that we can also decide how many lanes we should have in a highway bridge, and here chromosome can be lane and the shoulder width. You can now see that lanes and shoulder width are competing objectives. If you have more number of lanes, shoulder width would be lesser. If you have larger shoulder width, number of lanes would be smaller, because the area, the right of way for construction of road is finite. So it becomes a constrained optimization problem casted in the form of genetic algorithm. And again, fitness can be quantified, minimize cost, meet the capacity, ensure safety margins. So GA can also balance the cost and capacity in some constrained setting. Now let us look into one specific final example to get a greater understanding of genetic algorithm when applied to a real infrastructure problem, where we only would be able to measure relative fitnesses than the absolute fitness, as in previous example of fx equal to x square. So the problem here is simple, that we have 5 zones in the city: zone 1, 2, 3, 4, 5. So this is zone 1, zone 2, zone 3, zone 4, zone 5. And all these zones suffer from some problem of flooding. Now, to reduce this particular problem of flooding, you have to provide pumps and drains. And when you put pumps and drains, you have to invest money. And there are always going to be budget constraints. This is something we have discussed time and again in various optimization problem. So here it is said that whatever solution you do, its cost should be less than some 100,000 rupees or $100,000. Unit doesn't matter. Objective is to maximize flood risk reduction. See, sometimes when we start dealing with optimization, our objective is always guided towards money. Let us minimize usage of money or minimize the cost. But we have to read between the lines that what optimization problem is really asking for. Nowhere in the question it is written that minimize the cost. It is saying maximize the flood risk while ensuring that total cost should be less than 100,000. So if you are able to reduce the flood risk to, let us say, 99% while investing all the money that you had, it would be considered a feasible solution and perhaps the best solution. Then saving some money and not reducing risk to whatever is the maximum possible capacity. So with this built up around mind, let us start with the problem formulation. So here we will actually have much more intuitive representation of chromosome. That is, for each unit, chromosome coding would be how many pumps we are installing there. So we can install 1, 2, 3 drainages and so on. And we of course need to have the mapping of what is the cost of installation of individual pump in particular zone and what is the amount of reduction it will have. Now you can argue that all these are neighborhoods. Why installation of same pump, same number of pump in different zones have different cost? Because pump is not a standalone entity. You need to have a drainage system. You need to have its compatibility with the overall elevation of a particular place. Find the nearest drainage there. So it also becomes a hydrologic and hydraulic problem. So this is the downstream of that this cost table should have been coming from people who study urban hydrology or urban hydraulics, and it is given to decision makers. Now take a decision what you want to do, because one important aspect in infrastructure decision making is to give the possibilities to stakeholders then the verdict, because there may be certain operational constraints, there may be some budgetary constraints, etc., that may be looming into certain zones, and that is where giving options become important, and then infrastructure managers pick the best decision that meet most of these particular constraints. So now what we will do, we will start with a small population of 4 chromosomes. We initialize all of these randomly. So I'm sure now the confusion you had about binary to non-binary, etc., will also go away, because these numbers can be just put 1 pump everywhere. This is put 2 pumps in zone 1 and 3 pumps in zone 3 and so on. All these are completely randomly generated by computer, and I have no control that how computer will generate these random numbers. I asked it to generate 4 chromosomes. That's what it gave me. And here each entry of course means how many units are present in each zone that we are talking about. So for each chromosome, we will sum the risk reduction and the total cost. If my cost is less than equal to 100k, only then it's a valid solution. Otherwise fitness should be zero, even if it is reducing 100% of the flood risk, because I don't have that much money to install my solutions. So for example, if I install one pump everywhere, you can intuitively see that it is going to be a suboptimal solution, cheap but ineffective. So the reduction in risk is 25%. Cost is only half of approved budget. So fitness is 25, but it's a valid solution. Similarly, if I put 21312, reduction in risk is 49%. All these values are coming from the table that I showed you earlier. I have just summed them up. Cost is 89k, fitness is 49, and it is valid. So from 25 to 49, we already see that this solution is feasible and better than that. So later on, we will ensure that this solution leaves, or this population member gets eliminated or extinct from our original sample that we have done, because initial sampling, as I mentioned, we had no control. So this is the third chromosome that we had put 3 pumps in first unit, 2 to 1. You see that it was able to reduce 64% risk, but total cost of installation was 107k. So it becomes an invalid solution. Mathematically, I should assign it the score of 0. And finally, this also gave me the cost of 102k with fitness equal to 0 because of cost exceeding 100k. And as a result of which, I have current fitness as 25, 49, and others are 0. I will again apply the roulette wheel selection method. I will assign the probability of selection that these two parents are selected, and then I will produce an offspring out of these, and then I will see the fitness and keep on updating my original population space until I lose out all the diversity at the cost of having a great performance in the outlined objective function. So total fitness 74, chances that first will be selected is 33.8, second is selected 66.2. This exercise is trivial here because we only have two non-zero parents, so they are going to get selected. But for consistency, computer will not understand this break in algorithm, so we want to make sure all steps are represented, right? So this is a good solution, this is okay solution, so we will let them come together and produce two child 1 and child 2. Again, we use the same rule, or we can define our rule: first two come from here, last two come from here, first two come from here, last three come from here. So child 1 will become 2 1 1 1 1. So just to highlight this 2 1 comes from here, this 1 1 1 comes from here, so this comes from here, and this 2 1 comes from here. I will also highlight the second one. This 1 1 comes from here, and this 3 1 2 comes from here. So if this is clear, you now clearly see that why these child 1 and child 2 would have this specific chromosome that we have done after this crossover. And now what we will again do is that we can now apply some mutation. Mutation can be as high as 10%. Again, I said this is a hyperparameter. This is just to make sure that your algorithm converge faster. So you say that I will just randomly select 3 numbers and flip the numbers between 0, 1, 2, 3. So it becomes 2, 1, 2, 1, 1. So, and other child may remain the same, but again, this is all done probabilistically. So if you are running it on different computers without any specific seed, all your solutions would look different from each other, which is totally fine, because this is indeed a stochastic way to go towards the convergence. So this becomes our final offspring. After all the mutation, you can also retain non-mutated or mutated one, because ultimately you are searching for the best solution in your space. So what we see here is that we find that the cost is now 70k, validation fitness is 38 for one of the solutions, in second case 37, cost is 70k, both of them are valid solution with some fitness, etc. So overall we see that original parents had fitness of 49, new offspring has fitness of 38 and 37. Now what we will do is that we will do roulette wheel on all these four. and select best of the two from these four and let them produce the offspring. So slowly and gradually we will keep on improving the overall genetic pool of the population than just worrying about where we were left last time. So we have already eliminated two chromosomes which gave us fitness 0. So there is an improvement from initial set to this particular set where all of them are non-zero fitnesses. Now Ruleville would run here, next population would look like this, and we keep on doing this iteratively over computer in multiple for loops, etc. And finally we see something like this emerging, after which we do not see any improvement in the costs. So the solution look like 2, 3, 2, 2, 1. Now immediately there is a physical significance of this solution. 2 pumps in zone 1, 3 pumps in zone 2, 2 pumps in zone 3, 2 pumps in zone 4 and 1 pump in zone 5. It's a valid solution because cost is less than 100k. It is giving fitness of 56, way higher from where we started, way higher from intermediate offspring fitnesses that we had. So we would say that this is the best compromise we will do to achieve the fitness. Again, there could be a theoretical solution that can take less money and perhaps give us a fitness of 57 or 58. But as per our convergence criteria, we have to stop somewhere, and that's where we decided to stop. So now you already see that whatever I spoke in verbatim, that this is good for complex problems, good for global search, has flexibility, is parallelizable, no gradients needed, all of them were demonstrated here. Because our idea is to generate as diverse of a genetic pool possible, keep on finding the best representatives and settle for the maxima. But of course, there is no free lunch theorem, as we typically say in data sciences, machine learning, or any learning algorithm. So there is a computational cost involved. If you have very large number of population, large number of offsprings will be there, large number of mutations will be there. So you would be populating large number of fields with the genetic coding, encoding, decoding, as well as the fitness cost that you are calculating at each and every point. So think about it, that now instead of 5 zones, you are talking about 562 districts in India. This is going to be a really long chromosomal field that you have to deal with every time. There would be certain rules of mutation that will happen. Sometimes they may get stuck into local minima because these are all greedy algorithms. They do not know anything gradients. They don't know in which direction to move for overall best. So they may get stuck into local minima and never move out of that, or the convergence may not happen at all in anywhere vicinity to the overall optimal. They are very sensitive to the parameters. So for example, if you have very high mutation rate, you may be dancing around the optimality but never converge there. So they exhibit high parameter sensitivity. So we also do the hyperparameter search, that what should be the mutation rate, but that is something we will not worry about here. And of course, all these are nature inspired meta heuristic approaches. So there is no guarantee of exact optimum, but there is hope that it will take us closer to the optimal. And sometimes we may find that why it is even learning, what placement of pumps in zones have to do with biological evolution. So it becomes sometimes cumbersome for stakeholders to really understand why this is even working or why this is even trustworthy for an optimal solution. So this is where we conclude. We have started our discussions with evolutionary algorithms and genetic algorithms. We saw some examples. In our next lecture, we are going to have a similar discussion on particle swarm optimization, which is equally fascinating and equally powerful approach like genetic algorithm in the world of nature inspired meta heuristics. Thank you. Dear students, in our earlier lecture, we have looked into genetic algorithms theory, how it works, and what are its advantages and limitations. In this tutorial, we are going to see genetic algorithm in action for a small example that we would try to relate to infrastructure planning. The story goes again like this, that imagine that you are a city planner and you are tasked with the location of a new infrastructure project, which could be a water treatment facility, and you are dealing with multiple objectives, that you have to minimize the constraint, there are multiple constraints involved, as well as there are multiple objectives that are there in place. That is, you have to minimize the cost while serving the largest coverage as well as ensuring the maximum benefit. So what genetic algorithm help us do? It help us search for good solutions in large or complex decision spaces, and we will start with some randomly generated individuals where each of them would represent the candidate solution. Over the time, we will see that which are the best members of that population. These best members will produce the offspring by uh, crossover. We will also introduce some element of mutation, and finally we will keep on doing this exercise iteratively until we reach some finite number of iterations or the convergence criteria is reached. So again, the objective function that we are going to use is, let us say, is a two-dimensional objective function x and y, and here our objective is to minimize this function. This function is known as Ackley function. It's a widely used nonlinear function in two dimensions, and it is known that its minima is at 0, 0. If you see it at this function, you would see that taking derivatives, equating it to 0 for this function is not going to be as straightforward as we were doing for fx equal to x square plus y square and so on. And if we can understand this function, we can always write an equivalent infrastructure cost x and y if we have the exact information about the infrastructure planning problem that we are going to deal with. But now we are not going to worry about exact differentiations. So a quick recap, what are the steps that we did in genetic algorithms mechanics? The first thing was that we have to search for a solution in a given domain, x min x max, y min y max. It's a domain bound solution that we are going to search for. We will initialize our population. Since we are searching for the location, our candidate solution is also having x coordinate and y coordinate, and we can initialize some 20 population members to begin with, and for each of the individual or member of the population, we will calculate the cost. Here, since it is a minimization problem, lower is the cost, higher is the fitness, and we will assign rank to each of the individual that we have generated initially. Then what we will do, we will select the population or the most effective members of the population using some roulette selection or tournament selection or picking up top 10 out of top 20 and so on. We already learned about this in our theory part, so I am not going to go with the specifics of roulette selection again, but it's a probabilistic way to select the top individuals that we have identified. Once we have these top individuals, we will combine the genes from these two parents and produce a crossover to get an offspring. Once we have an offspring, we can also add some random perturbations to individual genes to get a new chromosome, that we would say that not the mutation has happened. We use this mutation to ensure that there is some element of randomness built into our algorithm. Finally, what we do is that we also ensure that some of the elite members in the population are represented. So we always copy a fraction of top solutions from one generation to the next, so that we always have top of the candidate solutions to get the answers that are closer to our optimal. And finally, we wait for convergence. It could be number of iterations, as I mentioned earlier, or some error tolerance that has been reached. Now, when I put it all together, this again looks like a very familiar Python script that we have been working on, where we will be installing lot of libraries. Here we are going to use NumPy, some plotting libraries, and we are going to generate a GIF file. So we are again going to use Imagio to do that. Here the function that we are dealing with is an Ackley function. I will be using this function multiple times whenever I have to demonstrate optimization in x and y domain. So here it consists of three terms. One is the square root of x square plus y square. Second one is a cosine term, and third one is the exponential term, and finally the function is sum of term 1 plus term 2 plus this constant e. Now this e is of course the exponential, the value of which is closer to 2.718 and so on. Then I have to set up my genetic algorithm. I always use this NP random seed 42 so that whenever I run this code on any machine, my results are reproducible, and I can replicate the exact results on different machines. I also recommend that whenever you are writing your code for research pieces or for learning, try to play with this seed so that there is consistency in how you are visualizing your results. To begin with, I start with this population size of 30, and I would go with maximum number of generations up to 50. And what I would do is that I will also define the bound -5 to 5, -5 to 5 both in x direction as well as y direction. I define some 20% mutation range and mutation rate and range as 0.5, and I always retain top 10% of population which are the most fit for the further iterations. So this is what we call as enforcing elitism in our algorithm. Then what we do is that we create some of these small functions that would create some population for us. Here we have to generate some 20 or 30 individuals. So we are going to start the algorithm randomly. So you see that NP random dot uniform would do this function generator function, the generation of population between the lower bound and the higher bound. And since you see that size is population size, which is n times 2, 2 means one is the x coordinate and another is the y coordinate that is being solved. Then we also define the fitness of each individual member. We already are using Ackley function. So what we would do is that we would pass x value, y value for each of the population member or individual, and we will get the fitness. You see that I use a negative sign in front of Ackley value because I am solving a minimization problem. Higher is the value of function, lower is the fitness, and vice versa. And then finally, I have to pick up some selection. Here I am making some random choice, that is out of whatever population I am getting, and I will sort them in some form of the fitness, and I am going to select the top 2 individuals at random, and then based on these 2 individuals that I would select, I would be producing the crossover and the offsprings using these 2 parents. So then we define the crossover, that how we take the crossover. We already learned about this in terms of mathematics, that is we would take the genetic material from parent 1, genetic material from parent 2, and we will randomly combine them. Here we are using uniform crossover, that is each gene from random parent is present. Even if the location changes, the offspring chromosomic material is going to be different. And finally, we introduce the mutation here. Mutation is again done randomly. So if you see that if a randomly generated number is less than the mutation rate, we already defined mutation rate to be 20%, only then mutation will happen. Otherwise, whatever offspring we got in the last step, it would be retained as it is. And finally, we put it all together and run the main loop. If you see, first of all, we create the population and we save all these population to ensure that at each time, even if we are producing the offsprings, we are still retaining top 10% of elite members into our performance output, so that we are not drifting away from best of the answers that we have found earlier. Then we will keep on sorting the population by fitness. Highest fitness would come first, and then we would always use the elites. That is, for whatever fraction we have defined, we would always try to retain these elites in the top fraction. And then what we would do, we will keep on doing the selection, crossover, mutation over and over again until we finally converge. So at every point we will keep on going into these iterations up to 30 generations. So each set of offspring will represent one generation. We will measure the performance for that set. We will then again find the two of the best solutions there, again produce the offspring. So number of generations also represent the number of iterations that we are doing. And once we have all our values here, we will just do some plotting. So let us run this. This code should have some runtime of around 19 seconds. And it has already found some best solution close to 0.000 at the, and the value of function it is giving is 0.01. You see that at third significant digit these numbers are present, 0.4 is here and 8 is here, but you see how fast it actually converges. In almost 40 iterations, 50 iterations, you would see that it is standing at a point. We already said that we will run this for 50 generations. So if I increase, for example, number of population individuals, of course runtime will increase. So I will make it 50 and I will make this generation size as 100. Then let us see that how fast or slow our code gets and what kind of answers it would return. The moment I make all these changes, all I have to do, I have to just press this run, and it may take bit more time. It already found a solution. You see that we were already very close to the global best in 0,0, and as a result of which I always use the phrase near optimal solution. So it will take us to near optimal and find the best solution that where each of the particle is located to, and finally it will create some interesting animation for us. So it may take couple of times. Yeah, you see that almost in 20 iterations, it goes toward the center. All these particles are now dancing. They are still finding the best solution. Two best would produce an offspring, may mutate, may not mutate based on the criteria. But now from the entire domain of -5 to 5, you see that at 100th iteration, all these red dots are closer to the 0 values. So this actually a very clear demonstration that how genetic algorithms learn for different functions, for nonlinear functions and so on. Thank you.